Okay. So again, hopefully that was ample time to finish the warm up. I appreciate everybody being here today. It's Thursday, so week has moved pretty quickly. If you ask me, we only have one more day after today. The original plan was for us to test tomorrow, but based on my conversations with the other two biology teachers, we have made the decision to test on Monday. So you guys get the weekend to finish up your assignments, to get some studying done, to use those warm ups and exit tickets to get exposed to the types of questions you'll be answered on the exam, or you'll be asked on the exams rather. And I really encourage you all to do that. So I think this is a good thing for you. I think you guys will appreciate having the extra time. The test will be Monday the 22nd. And that also happens to be the first day that 7 of you are scheduled to be in class. So it'll be a fun day. And it'll be a nice chance for us to kind of get into a different routine where I'll be teaching both virtually and in person. So patience is what I ask of you, and I will always give you patience. But that'll be a fun time, I think, and something that you all will benefit from. Today, however, we're going to continue our discussions from yesterday about osmosis. If you were here yesterday and you remember, then you know that our lesson yesterday was cut off essentially because it was a half day, and I underestimated the amount of time that we would actually have. So we got to go over some things today, and I want you guys to be active participants today. Make sure that you are asking questions. Osmosis can be somewhat of a difficult concept, especially the types of word problems that we will be doing. So I want you all to ask questions if and when you are confused, and also please be ready to answer questions. So today is February 18th, 2021. It is the 5th day of our 4th unit. We're going to continue our discussion about osmosis. The best note takers have their notebooks out and ready to go at the very beginning of class, and they write down information from this first title screen. If that's the title, the date, and the day of the unit, I think you are in a great place. You might also include the objective, which states that biologists will be able to explain how homeostasis is maintained in a cell and within an organism in various environments via osmosis. We do have an essential question. How does the cell regulate its solute concentration and maintain homeostasis in various environments? All right. So here's something I thought we might need to go over again today. So I went back and I edited some of my slides, and hopefully you all get a better understanding of what exactly we're talking about here. So solutes are typically molecules. For example, salt. We could also be talking about sugar. We could be talking about oxygen, carbon dioxide. But these are molecules that will eventually be mixed into a solution. The solvent is kind of like the background environment. Oftentimes, more often than not, the solvent is water. And in this class, the solvent will basically always be water. When we mix these two things together and we dissolve the solutes in the solvent, together they make a solution. So I just wanted to be clear about that. Please write down that equation of sorts at the top. Solutes plus solvent equals solution. I know these words look similar and they are also homophones, so they sound similar as well, but we need to be clear about the differences between them because we will start to throw these different terms around. Solutes are the molecules that are actually being dissolved in something. The liquid that is typically doing the dissolving is the solvent, and then the solution is the mixture of the two. So the solute concentration is defined as the percentage of the solution that is made up of the solute. And again, that could be salt, NaCl. It could be glucose, C6H12O6. It could be any number of things. The solvent concentration is the percentage of the solution that is made up of the solvent. Again, the solvent is almost always water. So here's our equation again. If we take the percentage of the solute and we add it to the percentage of the solvent, it should give us 100%. This is important because it tells us that if we know how much solute there is, or if we know the percentage of the solution that is the solute, we should easily be able to calculate the percentage of the solution that is the solvent. In other words, if my solution is 30% salt and salt is my solute, then my solution must also be 70% water, and water is my solvent. 30 plus 70 equals 100. If my solution is 5% glucose, that means that my solution must be 95% water. Very simple math there. My solution is 80% water, then my solution must also be 20% whatever the solute is. So please make sure that you are clear on this, that you've written it down. Does anyone have any questions up until this point? All right. So we defined this yesterday, but I wanted to provide another definition, and hopefully you all were exposed to this concept and this definition as a part of your warm-up. But osmosis is defined as the movement of water, specifically water, across the membrane that does not require energy expenditure. And so because it does not require energy, osmosis is a type of passive transport. Remember, passive transport, no energy. Active transport does require energy. All right. Oops, I didn't do that right. It's okay. So in osmosis, water will flow from regions of relatively high water concentration to regions of relatively low water concentration. And I say relatively because it's in comparison to one another. So we don't have to necessarily be talking about high water concentration as being 99% and low water concentration as being 1%. It could be 95 as the high mark and 92 as the low mark. It could be 10% as the high mark and 3% as the low mark. It's just a matter of relation to one another. Which one is higher, which one is lower in relation to one another. Now, keep in mind that water concentration and solute concentration have to add up to 100%. So this means that if you have a high water concentration, let's say 95%, then your solute concentration is low, 5%. If you've got a low water concentration, let's say 55%, it's relatively low, then you've got a high solute concentration, 45%. So if they are essentially opposites of one another. They are what's my word? Conversely or inversely correlated. As when one is high, the other is low. When the water concentration is high, the solute concentration is low. When the water concentration is low, the solute concentration is high. And again, solute percentage plus solvent percentage equals 100%. Do this really quickly. All right. That's better. Okay. So again, for example, if you have a solution that is 75% water, then it must be 25% solute. The two have to add up to 100. So again, guys, when we're taking good notes, at the very least, we should be writing down what is highlighted, at the very least. I do also encourage you to write down these equations that you're seeing as well. Solute percentage plus solvent percentage equals 100%. Okay. So solving osmosis problems can get a little tricky, but we're going to get a lot of practice with it. So let's say you've got your beaker, and a beaker is basically just a glass container in the shape of a cylinder. you will be told in these osmosis problems what the concentration of the solution inside of the beaker is. You'll be given that information, or you'll be given enough information to figure it out. You will also be told what the concentration inside of a cell or inside of a living organism is inside of that beaker, or you'll be given enough information to figure it out. So for example, let's say we've got a beaker and the solution inside of that beaker is 90% water and 10% solute. And inside of that beaker, there's a cell or a plant. It could be just any living organism. And that living organism has a solution that is 40% water and 60% solute. Keep in mind, you see these numbers add up to 100%. 40 plus 60 is 100, 90 plus 10 is 100. After we know what the concentrations are inside the cell and outside of the cell, what we want to do is figure out how water is going to move. Keep in mind, I told you on a few slides ago that water will flow from regions of high water concentration to regions of low water concentration. Water flows from high to low. So here, outside of the cell, I've got a water concentration of 90%. And inside of the cell, my water concentration is 40%. So where is the water concentration higher, outside or inside of the cell? Please send your answer to the chat. My question is, where is the water concentration higher, outside or inside of the cell? Excellent, Ardeja, thank you. Clearly, the water concentration is higher outside of the cell. It's 90% outside, whereas inside it's only 40%. So based on that information, which direction is the water going to flow? Remember, it flows from high to low. So is it going to flow into the cell or is it going to flow out of the cell? Excellent. Thank you, Ardeja. Yeah, the water is going to flow into the cell here. So when we're drawing these, and it's always good, folks, to have a visual representation of these problems. Leaving it all in your head is not a good idea here. We want to have a visual representation. It can be something simple like this, a circle that represents your cell, and then some type of square on the outside to represent the outside solution. So it's always a good idea. Once we figure out which direction the water flows, we literally want to draw an arrow to represent that flow. I'm drawing my arrow from the inside and it points into the cell. That represents water flowing into the cell. Based on that, I can determine if the cell itself is shrinking or if it's swelling. Obviously, just like a water balloon, if I put water into the cell, it grows. It swells up. Just like if I put water into a water balloon, it grows. And if I let water come out, of course, it shrinks. So in this case, water is moving into the cell. So what's going to happen to the cell? Will it swell up or will it shrink? No, it's not going to shrink because the water is flowing into the cell. So remember, when, just like we got to think about, just picture it, make it something familiar to you. Right? Whether it's a pillowcase, when you put a pillowcase in, or when you put a pillow into a pillowcase, the pillowcase swells up. When you put anything into something else, it gets bigger, right? So when you put water into the cell, when water flows into the cell, that's why we have our arrow pointing this way. When water flows into the cell, of course, the cell is going to swell up. It gets bigger. All right, let's get some more practice. I'm going to do a couple by myself here. So now I've got some missing information. I've got a blank here and I've got a blank here. I do want you all to draw these problems with me. Even though I'm doing them, excuse me, you should be writing them down in your notebook. So I'm going to give you 15 seconds to draw what you're seeing here. It doesn't need to be perfect, just something really simple. 15 seconds. Okay. So we've got some missing information here. We've got a couple of blanks. I'm told that inside of the cell, I've got a water concentration of 30%. And outside of the cell, I've got a solute concentration of 50%. But I'm not told what the solute concentration is inside of the cell, nor am I told what the water concentration is outside of the cell. But the good thing about it is that I know that solute plus water equals 100%. So if I've got 30% water, I've got to have 70% solute. If I've got 50% solute outside of the cell, then I need to have 50% water outside of the cell. So this is really just pretty simple math. They've always got to add up to 100%. All right. Now, I want to determine what direction the water is flowing. And I know that water always flows from regions where it is in a high concentration to regions where it is in a low concentration. So in this case, outside of the cell, I've got a water concentration of 50%. And inside of the cell, I've got a water concentration of 30%. So clearly, water is more concentrated outside of the cell. It's in a higher concentration. So that means that water is going to flow into the cell. So I draw my arrow pointing from the outside to the inside of the cell. And my last thing that I need to determine is what actually happens to the cell because of the direction of this water flow. When we know that water is flowing into the cell, that must mean that that must mean that the cell is getting bigger. It's swelling up. So this is how you have to attack these problems. Any questions about this so far? Does anyone have any questions or anything that is confusing so far? Thank you, Brianna. All right. So let's do this one together. If I've got 65% water, then what's my percentage of solute? Excellent, Ardesia, 35. Sorry, I skipped over it. But it told us that we had 75% solute, so that means we must have 25% water. So based on these numbers, which direction is water going to flow?
Outside the cell?
Wonderful. Yeah, the water is going to flow outside of the cell. So I draw my arrow to represent that. And so if water is flowing out of the cell, then what happens to the cell?
It's getting smaller.
It's going to get smaller. It will shrink. Good job. All right. Now we're going to add another layer of difficulty, but you guys seem to be grasping it so far. And this really isn't that much more difficult, but we're going to introduce some key terms here. So rather than just giving you the numbers, we're going to give you words to describe the numbers. So your key terms are here, and you should write these key terms down. Salt water. Salt water is going to describe a water solution that is basically balanced. It's got 50% salt, 50% water. Distilled water or fresh water is very diluted, which means that it is almost entirely water. We can just kind of assume that it's about 98, 99, even 100% water. There's nothing dissolved inside of it. There are no solutes. When you see the phrase strong solution, we should assume that to mean a very concentrated solution. So that means you've got a lot of the solute, whatever it is, and very little water. And then lastly, of course, if it says 5% salt, that means that it must be 95% water because the two have to add up to 100. So make sure you're writing down these key terms, especially as we consider these EOC questions that we'll have. You won't be told, oh, it's a solution that's 30% salt, 70% water. They're just going to give you key terms, and you're going to have to kind of deduce what the percentages are. Okay. So here's a good example of one of the questions you may be asked. A human cell with 70% water and 30% solute is placed in a beaker of a very strong sugar solution. What will happen to the cell over time? So what does it mean for a solution to be very strong? What is the water percentage of a very strong solution? What is the water percentage of a very strong solution? Not that, that would be the solute percentage. So what's the water percentage then? Thank you, Rudy. Yeah. The water percentage should be 10%. The cell has a 70% water solution. Outside of the cell is a 10% water solution. So which way is the water going to flow? Inside is 70, outside is 10. So which way does the water flow? Good, Ardeja. Yeah, the water is going to flow out. If the inside is 70 and the outside is 10, that means the inside has the higher water percentage. So that means it's going to flow out of the cell. And so what happens to the cell over time if water is flowing out of it? Excellent. Yeah, thank you, Ardeja. It shrinks. When water flows out of the cell will shrink. Okay, let's do another one. A human cell with 70%, oh, okay, that's the same one we just did, sorry. But it's, again, always good to draw it out. So 70% water percentage inside of the cell, 30% solute. Outside, because it uses that phrase, very strong solution, then we should just assume that the solution is primarily solute, 90%. And again, that was one of those key terms here. Strong solution is 90% solute and 10% water. So that means that the water is going to flow out of the cell and the cell will shrink. Okay, let's try another one. Antonio placed a saltwater plant in a container of distilled water. What will happen to the plant cells over time? So if this is a saltwater plant, then what is its water percentage inside of the cell? Use those key terms that you hopefully just wrote down. If this is a saltwater plant, then what is its water percentage? Do I need to go back to those key terms? One more time. If this is a saltwater plant, then what is the water percentage of that plant? Thank you, Ardeja. Yeah, from the key terms that we just wrote down, that means that its water percentage must be 50%. And it says that it's placed into a container of distilled water. So what's the water percentage on the outside if it's in distilled water? What's the, okay, so back to those key terms. Let's think back to those key terms. Distilled fresh water. Please make sure you're writing these key terms down. Distilled fresh water tells you that the water percentage is 100%. This is your pure water. When we say distilled, that means that it's essentially pure water. There's nothing dissolved inside of it. So I'm going to leave this up, guys. I need you to write these things down. All right, let's go back. So the container of distilled water, what's the water percentage on the outside? Wonderful, 100%. All right, so you tell me, which way does the water flow?
Inside the cell.
Good, thank you both, Brianna and Ardesia. The water is going to flow into the cell. And so what happens to this cell? Good, Ardesia, it's going to swell up. It's going to get bigger. Eventually, if it swells up too much, it can burst. And in fact, because this is such a big discrepancy, 100% versus 50%, more than likely that cell is, or that plant is going to die. It's going to burst. That's too big of a discrepancy. It's not good to place saltwater plants or saltwater fish into fresh water. Okay. A freshwater amoeba is moved to a saltwater environment. What will happen to the cells of the amoeba? So a freshwater amoeba, so what is the water concentration inside of the cell? Not 50. Remember, we're talking about inside of the cell. So inside of the amoeba, and it's telling us that it is fresh water. It's a freshwater amoeba. It is going to shrink. You're right. But let's see if we can take a step back and make sure that everybody understands why it's going to shrink. So again, let me just ask, what's the water percentage inside of the amoeba? If it's a freshwater amoeba, what's the water percentage inside? Thank you, Brian. It's 100%. And I excuse me, I accidentally clicked again. Outside, we're told that the environment is salt water. So outside of the cell, outside of the amoeba, it's 50% water and 50% solute. That's what we mean when we're saying salt water. When we say fresh water, we're talking about 100% water. So because of that, and Ardesia has already kind of done this in her head, water is going to flow out of the cell, and that causes the cell to shrink. So get good with drawing these diagrams, folks. That's really going to help you out in the long run, rather than trying to do everything in your head. Once you get really good at it and you fully understand what is being asked, then probably you'll be okay doing these problems in your head. But in the beginning, we really do want to focus on having a visual representation of what we're being asked to analyze. All right. A cell with 80% solute concentration is placed in a beaker with 40% solute concentration. What will happen to these cells over time? So I'm not going to ask you guys to go step by step now. I just want to see if you can give me the answer. So I'll read it one more time, a little bit slower. A cell with 80% solute concentration is placed in a beaker with 40% solute concentration. What will happen to the cells over time? Go ahead and give me an answer in the chat. I'm not going to go step by step this time. Any answers yet, or are you guys still drawing it out? What's going to happen to this cell over time? Okay, good. I've got an answer from Rudy. Rudy says that the cell will swell. Anybody else have an answer for me?
I agree with her.
Good. Thank you, Brianna. Gonna wait maybe 30 more seconds. Ardeja says swell as well. So we've got 3 folks who are saying swell. Brian says swell as well. Okay, excellent. You guys are all incorrect. No, I'm just kidding. That's the correct answer. The cell will swell. So let's take a look at this. If it's 80% solute concentration on the inside, then it must also be 20% water concentration. Got to add up to 100. If it's 40% solute concentration on the outside, then it's got to be 60% water. Got to add up to 100. So the water percentage on the outside is far greater than the water percentage on the inside. It's 3 times greater. That means that water is going to flow into the cell, and that's going to cause the cell to swell. Excellent. All right. So there is an exit ticket. There is also an asynchronous assignment. So I've got to add something there. Give me 1 second. But you guys have 20 minutes or so to get these assignments done. That should be plenty of time. U4D5, especially those of you who were engaged today. Excellent job, Ardeja. Excellent job, Rudy. And I appreciate Brianna as well. Brianna, thank you for contributing at the end there. Those of you who were practicing and actually writing these things out are in a good place to do this asynchronous assignment. Let's see what it's called. So far in Unit 4, we've got 5 asynchronous assignments. Please don't neglect the exit ticket as you're working. What block do we have to be in? It's second block right now, Kathy, if that's what you're asking. We're still in the same. Yesterday was a half day, so that's, that was a little confusing for folks, I think. But today is the same normal schedule, and then Monday we're going to switch schedules a little bit again. But I'll talk about that tomorrow. I'm glad you brought that up. I need to edit my Canvas course over the weekend.
It's because one of my first block teacher got me confused.
What did they say?
Because he was telling us, he showed us the new schedule for Monday, and he said that's today we were starting that. And so that's why I have been confused this whole time.
Yeah. Let me not be rude, but some people, we had a meeting yesterday in which everything was kind of explained to the teachers about our return to school next week. And some people just weren't listening very well. So I don't know who that teacher is, but I think when the adults aren't on the same page, then obviously the students are not going to be.
So I have been confused this whole entire time. Like, I would be going by the schedule.
Yeah, nothing's changed so far. Monday is when we're actually going to change. So this class on Monday will meet at, give me 1 second. I think we meet at 8:37 or something like that. Give me 1 second. 8:34. We start class at 8:34 on Monday, and then we'll be done at 9:49.
Okay.
Tomorrow is the same day. Same thing. Tomorrow we start at 10:20 per usual.
Okay.
Okay, folks, it's now 11:35, so you all are good to go and enjoy your 30-minute lunch break. I appreciate everybody being here, and I'm thankful for those of you who participated. Great job today, Ardesia and Brianna and Breon and Rudy. Others, please make sure that you come back ready to participate more tomorrow. We will be reviewing the entire unit in preparation for Monday's exam. Have a good day, and I will talk to you all tomorrow. Peace.